Hello, everyone, and welcome to another ACE Talk. Today we have Peetak. We're very excited for this, giving a literature review on ML and climate science. So just to introduce our speaker, Peetak, he's a doctoral candidate at the University of Massachusetts Amherst. His research interest is at the intersection of machine learning and computational fluid dynamics. In 2019, he co-founded a data-driven consortium called IceNet, which develops predictive machine learning algorithms to improve engine design and accelerate computing in fluid modeling. Recently, he spoke at NVIDIA GTC 2020 and co-organized an ICLR workshop on climate science titled Tackling Climate Change with Machine Learning. So I'm very excited to have our speaker here, and Peetak, feel free to take it away.
Thank you so much, Susan, for the great introduction and for the opportunity. Hello, everybody. I hope all of you are doing well and staying healthy during these uncertain times. Thank you so much for joining in for this talk. Here, I would provide a brief, very high-level overview of the machine learning and climate modeling, given that in an hour time is not enough to even talk about climate modeling in itself, how intricate, how complex it is, and especially the advances of machine learning in this area. So I'll try to do my best in terms of providing a very high-level overview so that everybody can understand where this field is at and where it is going. So before I go ahead, I just wanted to share this image of the Earthwise that was taken by the Apollo astronauts, which actually started the modern environmental movement. And this led to a lot of the stuff that we see around us, like the Earth Day and the current state of the development and interest in predicting and the climate, as well as preserving it. So we hear about this a lot in the popular media, that is artificial intelligence the savior of the global climate predictions? And can it really predict extreme events, or can it really predict climate change, how it's going to impact the different parts of the world and different communities? So while there is some truth to this, this answer is a bit more complicated. So I hope in the next few slides, in the next few minutes, I can provide some overview of why climate modeling is so complicated, what are the challenges, how machine learning can help, and how you can help in this fight. So the outline of my talk would include a brief climate tour, which would provide an overview of what climate modeling is, how complicated it is, the different interlinking systems that kind of like drive our climate, or the processes in it, and why is this really hard? What are the challenges? And I'll talk about it briefly, just to give you a sense of why we have such a difficult time in predicting climate, in predicting climatic events. I'll talk about some state of the art in machine learning for climate, some different areas, and some very exciting work in all of these different areas, just so that you can get a sense of where the field is and what kind of technologies we use, especially most of, I believe the audience is from a machine learning background. So this would help you kind of relate your experience in image or speech to what folks are doing with climate. And lastly, I'll briefly touch upon how you, the participants, attendees can participate in this endeavor. There are multiple opportunities out there, and I'll talk about it at the end of the presentation. So coming back to the climatic system, here this cartoon from Hack and Gettleman kind of like provides the emphasis of how complicated the system is. So here on one hand you have the atmosphere, and this entire climate system is an interaction between the atmosphere, the ocean, and the land biosphere. So here you have the greenhouse gases in the atmosphere, or which are absorbed in the ocean. That leads to some carbon burial or melting of the sea ice, for example. And sea ice again is a big mechanism to reflect some of the solar radiation that kind of falls on it. And with a depleting sea ice, more solar radiation is absorbed by the ocean, heating up the oceans further, kind of creating a feedback loop. And also you have the land and biosphere that kind of impacts the atmosphere as well as the ocean, because given the land profile or the land usage you have, it can lead to different levels of back radiation back to the atmosphere, as well as different nutrient that goes into the seas. So as you can see here, it's a very complicated system and it's very intricate, that makes it really hard for any modeling paradigm to kind of like predict for longer time periods. Another thing that really kind of impacts all of us is this poleward heat transport. Without going into too much details, the basic idea is that the Earth is not heated uniformly all over its surface. Some parts of it are heated more, some parts of it are heated less, like the poles. So that leads to the energy movement between the poles and the poles and the equator, and which drives the atmospheric and ocean circulation systems that really are the drivers of energy as well as life on Earth. So, and again, this is a very complicated system, as you can see from this particular cartoon. The other thing that, apart from the natural variability in climate, the other thing that we all know about is this particular. This is the video that I wanted to play. So this is the global temperature anomalies, which kind of is an outcome of the greenhouse gases that we're putting into the atmosphere. So on the left side is the famous hockey stick curve, this famous hockey stick profile here at the end, developed by Mann et al. From NASA, which actually correlates the temperature of the surface temperature of the Earth to the carbon dioxide that is present in the atmosphere, and show that as we pump in more greenhouse gases into the system, the surface temperature of the Earth kind of increases. Something that this particular video on the right, which is again from NASA Goddard, kind of shows that as some of the hottest years on record has been in the recent past, and that kind of shows that we are in effect putting and forcing the climate patterns and the system externally, such that it is affecting the natural variation of the climate, which is what we see from this graph and from this plot. So I'll just let the video play and show this particular snapshot when we reach towards the end of this, where you see that there is an asymmetric heating over the land surfaces as well as in the oceans. One thing that we need to remember is that oceans absorb about 93% of the carbon dioxide that we put out in the atmosphere. So and that in the end heats up the oceans, causes gasification, causes issues with coral bleaching and things like that, and that has another effect on the climate system itself. So this is again a very complicated system for multiple reasons. So one thing that we should potentially discuss, and this is a point of confusion between many between many members of the audience, is that what is the difference between weather and climate models? So while weather predictions are are done for very short time scales, like for a day, a week, maybe 2 weeks at a time, and it's the idea is to determine the current and future atmospheric conditions at a very high resolution, which means at a very at a city level or a town level resolution, done over a very short time period. And typically this is very data driven. Google AI has done some excellent work in this space, where they use some tools to forecast the cloud patterns and things like that based on current data. And typically one could use a Monte Carlo simulation or things like that to predict some of these things. Whereas for climate models, it actually is an extension of the weather predictions, but also it's done over a much longer time span, like years. We're talking about decadal time scales, and these include a lot more physics. These include a lot more physics of the say radiation here, like this cartoon here from 21 kind of shows that you have to conserve energy. You have species transport, for example. You have different greenhouse gases in the atmosphere that has an effect. You have the land profile, the land usage profile has an effect, like the back radiation, the amount of back radiation and the solar incoming solar radiation, depending on the natural variability of the sun itself. So climate models are far more complicated than weather models. So we should not confuse them together. And I'll talk about a bit more about what climate modeling entails. So what are
Peetak,
the challenges? Yeah.
sorry. Hello. I have
Yeah.
three questions here, actually. Just
Okay.
if you could flip back to the previous slide. They had a quick question about the video. If the red is more of a delta, or is it like the like absolute value of the temperature, right? Because I do see that maybe like the more North Pole was red at the end, but it doesn't mean that the temperature there is higher than the rest, right? Is it more like a percentage change rather?
Yeah, so it's percentage change based on the local baseline that started in like 1900s. So if you see that the scale is really small, so it says degrees Celsius and it goes up to 7. So it just shows that the pole, because it's cooler, and there is this, because of this poleward heat transport, because given the Earth is not heated in a very similar way, not a very uniform way, what happens is because of the higher heating and obviously the higher concentration of greenhouse gases, this part of the Earth is more heated, which kind of drives the convection to the cooler parts of the Earth, which is the poles, and they kind of like assemble and kind of like align and sit on the poles than on the tropical regions. So yeah, it is the delta with respect to the baseline at that particular temperature, particular location.
Gotcha. Thank you so much. So for the next slide, there were a couple of questions as well from the audience. The first time is from the time spans, like the shorter time spans and the longer time spans. Like how long is that again? Is that like decades, or the
Sure.
audience just wanted to clarify?
Sure, it's typically so. What they do in climate, modeling is that you have certain, you understand the processes that affect climate, and you have certain certain maths that you have carved out, like partial differentials or things like that. And then you try to build a model based on that. And I'll talk about it in the next few slides, how these models are made. And then what you do is you do backtesting on that over, for example, the ice core data that people get from the Antarctic or the Arctic. They drill ice in the in these regions and kind of know what is the percentage of CO2 or other gases that kind of like is trapped in these ice cores, and they use those as the target variables in a way, and kind of tune their model parameters in a way that they can backtest and get the right solution, going back decades and hundreds of years, tens of years. So yeah, I mean, it actually, using that backtesting, once you have a model that kind of works well, then you try to project in time over like 10 years, 20 years, 40 years, 50 years. Obviously, as you keep going, further away in time span, the predictions kind of have a cone instead of a particular definite value, because there are uncertainties in the model that kind of creep in at that point. So yeah, it could be, typically they are decade on a decadal time scale, like 10 years, 20 years, 50 years, 100 years. That's why we hear about in the news that in the year 2100, the Earth will be this much hotter or whatever, and these kind of comes from these models.
Gotcha. Thank you. One last question here. So is again comparing the more shorter weather predictions and maybe the longer term climate models. Like, do the features used differ a lot between these? Because I imagine the weather predictions might have some sort of real time data or something that is less applicable or informational to longer term.
Sure. So for the exactly, I mean that's a very good question, and that is what I think a lot of people kind of get confused. So I think this would really help, hopefully, that in weather predictions you start off with a very deterministic system. The weather today is going to be particular, in a particular state, and in weather you're not trying to predict a lot of things. You're just predicting some humidity, some possibility of rain, some temperatures, things like that. And you're only predicting it on a very short time scale, like 1 day to 14-day period. Obviously, the closer you are in your time scale, the more accurate your predictions are. That's why we tend to get the predictions over the next 2-3 days more accurate than over a longer time period. And that kind of has its basis on the chaos theory, where these are nonlinear systems. So if you have a change in initial conditions, you tend to get much different final outcomes. So the things that you use in weather predictions are obviously some of the stuff like the humidity in the particular region, the wind flow, and things like that. Whereas in a climate model, those things are very different. You take the the natural variability of sunlight, for example, in a particular over the entire Earth, and you take that into account. You take so it's on a much bigger scale, the climate models. Weather predictions are on a much smaller scale, so you take much different kind of variables as your input. Just to give you a gist, I can go into details of what kind of inputs typically they take, but they're very different usually.
Gotcha. Thank you.
Okay, so the thing is, why is climate modeling so hard? What makes it such a challenging problem, apart from you're trying to solve at some point some form of the Navier-Stokes, which is a nonlinear PDE, and there are all the interactions are in terms of differential equations, PDEs, ODEs. So it is a very, very complicated system mathematically as well. The other stuff that kind of really affects us is something called as external forcing. So what is an external forcing? External forcing is the stuff that we put out in the atmosphere or in the ocean. For example, the greenhouse gas emissions. Here is an example where depending on how much industrialization happens and how fast it happens, and how much greenhouse gases we put into the atmosphere, it kind of acts as a source term in the equation, and it affects the solution as propagation as well. Also, the land usage over time. If we if we have plant a lot of trees and build a lot of like forests in a particular area, that land would reflect much less heat back, and that would become a big factor in that needs to be modeled. And deforestation, on the other hand, kind of leads to the opposite effect, where the land tends to get hotter and drier, and you have issues of encroaching deserts and stuff like that. So because the land gets much drier. So and the other impact is the natural variability impact, which is we all know that the Earth goes around the sun in an ellipse. So we have, at some points, we are closer to the sun, and at some points we are farther away from the sun. So this kind of leads to a natural variability in the solar alignment and the radiation that the Earth or each part of the Earth receives, the seasonal alignment. And that is pretty much known over the years that this is what it would potentially get. But unless you have some activity like a volcanic activity, which would, throw in a lot of gases like sulfur and other gases, and a lot of heat into the atmosphere, which would potentially change some of the predictions in the climate. Like, for example, like for the ice ages and stuff that happened in the very distant past, some of these activities were related to volcanic eruptions and things like that. So this makes climate modeling very, very challenging, because not only there are issues that we cause, like land usage and greenhouse gas emissions, and there are issues that the Earth itself or the nature itself causes. So to give you a sense of how what the chaotic nature of the natural variability, and this is from Edward Lorenz. Edward Lorenz is famously known for contributing a lot to the chaos theory, and some of the basic when you build a climate model, some of the first tests you do is on some of these Lorenz systems, 69, 74, things like that. So the idea here is that you start off with an initial condition, which could be in this particular small blob, and based on that you determine a particular forecast. And this is deterministic in nature, because you have an initial condition, you get a particular outcome in this particular sphere. But what if there is some some error in your measurement of the initial conditions, like the temperature or something, the pressure, the precipitation, or the wind, or things like that. What happens is that then you need to also account for the uncertainty of the initial conditions, and that kind of leads to a big forecast uncertainty over a longer period of time. And as you progress in time, this forecast uncertainty kind of grows. And this is only because of this is only the effect of the natural variability. We are not even counting the effect of the external forcing, which is something that we cannot decide. For example, during this COVID time, we see that the cities are looking cities have much lower pollution levels. The industrial output has really gone down right now because of the lockdowns all around the world. And that will have some effect in the near term on the weather and the climate, and that is something that you cannot plan for. So just shows that how difficult it is because of the chaotic nature. There's so much interrelationship between all these different factors. So in an Earth systems model, what you do is you build ground up all these different dynamical, physical, biogeochemical subsystems. How the soil is going to behave under different conditions, how much moisture it will retain, how much moisture will be evaporated, for example, what will be the runoff, and things like that. And you build on all these subsystems together, and you build ground up from there to build an Earth systems model. So a truly good Earth systems model, like one here shown, which is called the E3SM, is one of the best tools in modeling climate. Big problem with that, it's very, very computation expensive. You cannot really, build these. You cannot really do these things at a much lower, much higher resolution, and therefore really lose, accuracy due to the very expensive cost of computing this. So here is where machine learning or things, statistical analysis can really help. And I'll talk about some of these things in the next few slides. So what is the big challenge of climate data? Some of the big challenges included spatiotemporal. Many problems in machine learning are spatiotemporal, like for example in robotics or from video recognition, things like that. Those are some spatiotemporal problems, and here as well in climate data, these are spatiotemporal problems. These are very high dimensional problems. They are obviously unlabeled. They have issue of missing data, because when you get experimental data on all these initial conditions, for example, you always tend to miss some parts of it because of failure of the recording instrument to record all these data sets. And it is a time series data. It's heterogeneity, which means it's not heterogeneous time data, which means it's not uniform in its intervals, which makes it harder. Like for example, we all know that how recurrent neural networks or STMs have a degrading performance on heterogeneous time series data. So this makes it really, really hard to kind of like use some of the canonical machine learning algorithms to climate data sets. Obviously, there is a big interrelationship, and also the complex physics that kind of has a big effect on the outcome of this particular prediction ability using machine learning. So here I'll talk about some few examples, and this would hopefully give you a sense of how machine learning is being used in the community for different things. So for example, I'll provide some 6 examples here. So a couple would be from something called as emulators. So emulators, the idea behind emulators is to build very cheap and very fast surrogates. What do I mean by surrogates is it is a machine learning model that can somehow give you a ballpark assessment of the physical process that you're trying to model. And this kind of helps in decision making, helps in things like sensitivity analysis and things like that. And I'll talk about 2 examples here. One is trying to build an emulator for an entire global circulation model, GCM, or for subsystems or subphysics such as the El Nino. El Nino is the unusual warming of the Pacific, East Central Pacific near Ecuador, Peru, that happens fairly regularly these days, which actually has a very adverse impact on trade winds, as well as has a very adverse impact on monsoon in Asia, South Asia, which is very dependent on the seasonal rain to irrigate and also ensure that they have a good crop during the fall. So, and I'll talk about super resolution. I think a lot of you would be familiar with some of this work, especially coming from an image background. I'll talk about some forecasting because it's a time series. So the big idea is to be able to somehow forecast some of the climate variabilities. I'll talk about one work that I presented at GTC recently. So it's my work on how machine learning could be used for model calibrations. For example, as I said, all these global circulation models or Earth system models have all these submodels that are stacked on top of each other and built ground up. So if the model submodels are wrong, you cannot expect to get a right prediction at the big global circulation model level. So this is an effort to kind of fix some of these submodels and ensure they have a sound and deep physics background. And also there is some work that exploits the causal relationships between different features using deep learning that I'll talk about. So let me start off with the first example. So this is an accelerated simulator.
Sorry, just to cut in, there's like 2 questions here, actually, from the last slide.
Okay.
Yep. So the first question is, are the surrogate models, like in the emulator part, are the surrogate models like ML models that complement the climate models, or do they replace, or what is their relationship?
That's a very, very good question. So there are people are doing this both ways. To answer it, briefly. So the examples that I'll show you here is the replacing pretty much the entire global circulation model using a surrogate. But obviously, it is very, very limited in its scope because it cannot learn from outside the distribution of the data that it has been trained on. So these are very limited, but because sometimes what happens is we want to redo some of the same simulations again and again to determine the sensitivity of certain physical process on the final outcome. So for that, we don't want to run an entire GCM again and again because it's very expensive. So there, these fast surrogates will help because there we can actually see the sensitivity of, say, for example, the radiation model within the GCM to the final outcome and things like that. And people are using it the other way too, where folks are using it only for a part of the model, which is kind of comes back to my work here in this area, where we are looking at some emulator models that we are using to replace some submodels for GCMs. And what that will do is that will only give you the accurate solution on some of these sub-physical processes, and not the entire global, not at the global circulation level. So yeah, the answer is both.
Gotcha. Just like to follow up on that one, they asked, is emulators using predictive modeling like as the simulation? Like, let's say you take in some features and then you start running predictive modeling for a period of time and using that as maybe simulation for the future to evaluate a climate model.
Yeah, I mean, that is something that they do. So they use the high fidelity solution that they get from these global circulation models as the ground truth, and they train their models on that. And I might as well pivot and show this particular slide. I think this would be of interest to the individual that asked the question. That what they do is they use the simulation data sets from these global circulation models, and then build machine learning tools. This is a pretty simple CNN network that they use to kind of replicate that entire process, and then they obviously try to forecast in time. But the thing is, so different projects have different goals. Like typically, some of these projects do not aim to forecast in time. For example, here the idea was not to forecast in time, but there are certain projects that I'll talk about in the next few slides, which actually want to build emulators and then they forecast in time. So yeah, the answer is again both. It's like people are still kind of figuring out what is the best way to do this. It's a very new area of using machine learning in climate models. So people are actually doing like pretty much everything right now.
Gotcha. Thanks so much for the answers.
Yeah, sure. So here again, this is a work by Kasim et al., and it's called Deep Neural Network Search. And you will hear from Kasim in the next few weeks. He is giving a talk at the end of this month about his work. And in this work, what they do is they, instead of, as I mentioned earlier, all these physical processes have a lot of different submodels in it. And sometimes you want to see what if you change the, just remember this particular kind of plot. So if you change certain things in the initial condition, does it really, what is the forecast and uncertainty it gives, and how much sensitive that particular parameter is to the forecasting ability of the model itself? So you want to understand that, because there are too many parameters at this point in a GCM. So what this emulator does is that this kind of replicates the simulation behavior from an entirely neural network approach, and they are comparing the energies, they are comparing all the different important criteria that kind of needs to be matched, just to ensure that it's just not a data matching but also physics matching result. Because in physics, all too often, you cannot just copy a data, like you just cannot map a data. You have to ensure that the data makes physical sense. So some of these things like power spectrum and other things kind of give you a sense of how the data set is actually physics relevance, the physics relevance of the data. So and by doing that, they look at the simulation time and the emulated time. This is quite a few orders of magnitude of acceleration that you kind of get in this particular by doing this particular exercise. And what this kind of leads is to ensure that you have some faster sensitivity analysis for the GCM model. You can actually go into submodels and then change the parameters, for example, and see what kind of predictions it will give. Does it really change the answer that much, and things like that. So this really kind of is an ancillary tool to kind of use alongside your GCM model to see what parameters have really big effect under certain conditions and things like that. So this is one area where the community is heading out, and they use tools like pretty simple convolution neural networks, and you will find more details in this particular paper. And if you're interested, he's actually going to give a talk in the next few weeks. So the other kind of work that folks are doing in this space is to build an El Nino emulator. So for folks who do not know what an El Nino is, it is a unusual warming of the oceans, the Pacific Ocean primarily, off the coast of Peru and Ecuador. That kind of leads to an abrupt change in the monsoon patterns over East Asia, which is not as well irrigated and depends on naturally occurring rains during the summer months for irrigation and for cropping. So these guys this is the work from Mahesh et al. And shown at NeurIPS, where they actually used some of these simulations, like this is a particular GCM called AOGCM as the ground truth, and that is the most expensive part, and they obtain it from their collaborators at some national laboratories. And then they use a mix of a convolutional autoencoder and a recurrent neural network architecture to predict the time series of the El Nino index, which is a particular quantity of interest that kind of gives a sense of if the El Nino will be strong or poor. If it's more than zero, for example, if it's less than zero, for example, in 2008, the El Nino was very weak. And for other years, the El Nino is quite strong, which kind of correlates really well with the heating of the surface temperature of the Earth. We see more and more positive patterns of El Nino every year. So you see that the climate AI model kind of predicts really well with a very, very limited set of inputs, and gives a sense of when the El Nino would happen, to what degree will happen, and also this forecast inference is super cheap over physical model, where you can predict it at honestly a fraction of a cost. So the big application area in this, and some of this work has also been done by the Los Alamos National Laboratory, the Earth Sciences Division. The big application area for this is to kind of inform as well as educate the farmers in these particular vulnerable areas in Southeast Asia and South Asia on how and when they should plant their crops because of an impending El Nino, as well as also the government and the local authorities, so that they can provide support to their farming communities if they're expected to have a much poorer monsoon that year or not. So these kind of emulators really kind of have a role in decision making in today's world. And it is pretty exciting to see a lot of the big national laboratories kind of like as well working in this space to predict and help out folks in terms of what is expected in the local climate due to some events like such as this. So this is a very exciting area of research in this community of climate. So the big reason for this is that climate data is often times at a very low resolution, which means that, for example, weather, as we talked about, is done at a very high resolution for a much shorter period, because the cost of doing that is not as prohibitive. Whereas the climate data sets, climate modeling, where you are trying to model the entire globe or a particular region of the globe, and where you are including so much of the physics and physical processes, it becomes very hard to do it at a much higher resolution, which means information is often lost or not often available for areas or for regions that are within that low resolution. And by low resolution, I mean of the orders of few hundred kilometers mesh size. So here is this very exciting work from Lawrence Berkeley Laboratory, where they are using something taken from the world of image, where they are using super resolution techniques like SRGAN and other stuff, GAUGAN and stuff, and actually upscaling the low resolution inputs to predict something like what would be the equivalent of a high resolution output. So they use a bunch of encoder decoder systems and a lot of ResNet blocks. And the final outcome of this is to artificially enhance the quality of climate predictions locally, so that you can have more information about how a certain event or how a certain region of interest would evolve over time in terms of because of the climatic changes. So this is a pretty exciting work, and I have some. I'm doing some work in this area too, and this is very interesting in terms of the applications or the ability to kind of feedback into the global circulation models. So the other.
We have two questions here. Once again, sure. So for this slide is kind of is it kind of like a data enhancement or data augmentation using more sparse data and creating more high fidelity or high resolution data?
Exactly. That is the perfect summation of this. Exactly.
Okay, awesome. So for the more previous slide before this one, there was a question of what is the intuition about why the scaling of using a CNN is better than physical model? So, or maybe they mean RNN. Yeah.
Yes, okay. Yeah. So the thing is, you are so sometimes. So I don't exactly, this paper used some physics information as well embedded in the CNN. So it's not like it's just like data copying, trying to map the data from one part to the other. That's a very difficult question to answer because, we really don't understand climate models, per se, what some of these features would affect. Some of these features kind of interact with each other. And on top of that, you put a neural network, which is, in a lot of ways, a black box either, or at best a gray box. So it's a very difficult question to answer. Why is this better? One of the reasons could be, the higher number of parameters in a CNN, which could potentially explore more relationships that some of these PDEs and ODE coupling cannot. That is, I think, what comes to my mind. But yeah, that's a very interesting question, and I think a lot of work is going on in this space where folks are trying to query these CNN models in terms of trying to do, use TSNE or things like that to understand what did these models learn, why did they learn it, and also, CNN, the convolutional kernel in a CNN could be used as a numerical stencil. For example, if you want to kind of impose a physics restriction like a second order derivative or things like that, you can do it using a convolutional kernel. There is a lot of work out there. So one could potentially do that to enhance the physics understanding of what they are getting in terms of the output from these simulations. So yeah, I don't have a better answer than that, but yeah, that's a very good question. Yeah.
Yeah, that's very helpful. Thank you.
Okay. So moving on, the other kind of application that the community kind of is looking at is to, because all of the climate data is spatiotemporal, you have a time series, basically, an irregular time series. So what folks do is they kind of want to predict certain quantities of interest. For example, in this case, this work is from Nadiga at ICLR 2020. And the idea is to predict the surface temperature based on some Earth sciences Earth systems model. NCAR is the is a big leader in this area. To use their model data as a ground truth to predict the surface temperature predictions, back testing on some data sets. So here, what they did, they kind of used an ensemble of models, different models. They used an LSTM, Conval STM, PCA. They reduced the data. They did a model reduction on the data set and used an LSTM on top of that. Just used a fully connected layer kind of network and used some statistical models that is currently used in the community. And what they see is that, to predict some of the evolution of some of these quantities of interest beyond a particular time, for example, the 8-month period, it's really difficult. And some of these models even don't do a good job at that. For example, model reduction and LSTM and LSTM in general does not do a good job at that. Whereas some of the other models like Conval STM and stuff tends to do somewhat better. So yeah, this is and the reason for that is the complicated physics and the complicated interactions between some of these physical processes. For example, if you see the error plot from this paper, they have a larger degree of error on the surfaces of the Earth, which kind of makes it obvious that the processes of the land usage, for example, the land usage was not taken into account in the model itself. And that kind of makes it complicated, that this is just not a simple time series. It has to incorporate some sort of information about some of these pixel level data that the land usage, as well as the if there's a forest, if there is a desert, things like that can actually have a big impact on the predictions. And the idea in this particular approach is to kind of do a long-term predictions of the quantity of interest, and it's an evolving area in this space. So the next work is from my work that I showed at GTC and at NeurIPS last year. And this work is kind of takes a different approach. Rather than kind of building an emulator for the entire global circulation model, which is harder, obviously, and as the person, the individual asked a few minutes ago about why these models tend to work better, we typically do not understand why that happens. So this is a different approach where we, instead of trying to model the entire GCM, we model some sub-model within the GCM. As I mentioned earlier, that these global models, the Earth sciences models, have all these sub-models kind of stacked on top of each other and building ground up from there. So if you and some of these sub-models have parameterizations or calibrations of these model parameters done on very canonical experiments, which means that they are very, sometimes they do not work well outside of the distribution of the data. Sometimes they do not work well if for the real world cases. So in this approach, what we do is we build a data set using high performance computing and solving the actual Navier-Stokes. This approach is called direct numerical simulations, and then from that we extract some data sets and we reduce it based on some physics that we care about, and we have different data sets in that particular from that we extract from this particular simulation, and then we use some form of neural network modeling. Here in our approach, we use a neural ODE because the relationships that we're trying to model can be modeled as an ODE. A neural ODE, has if you are familiar with this line of work, it uses a network as an it parameterizes a network as an ODE and makes predictions based on and makes a functional mapping between the inputs and the outputs based on that. So we use a bit of modified architecture on the basic neural ODE and enforce physics constraints like energy, for example, because conserving energy, conserving mass is very important for all these physical systems. And then we evaluate these models in an a posteriori setting where we have a totally unseen test case, and we see how the model performance is. And just to kind of sum it up, the dots are from the model predictions, and the solid lines are from the actual ground truth. And we see that the predictions are really, really good for an unseen test case. Happy to go into the detail of this work, but it would probably take an entire presentation on itself. So the idea here is to kind of improve some of the submodels that can plug back into GCMs, and then trying to improve some of these sub-blocks one block at a time. And over time, you will potentially have a very data-driven or with physics embedded information in these systems that can actually predict, that can actually make better predictions, thereby improving the predictions of the global circulation model itself. So moving on, this is one of the very interesting researches that I kind of came across recently, which is to use like causality or explainability in machine learning is a big area these days, especially for time series. And there are a lot of work out there, especially for time series, like Granger's causality and things like that, that the financial, the world of financial modeling uses quite often. So here they kind of build on that, and they used this particular tool called PCMCI, which is a two-step causality model. And then they build this framework to identify relationships between events that are happening all across the globe and to climatic events that are happening locally. This kind of, has the potential to provide new insights that we probably were not aware of, because one thing that we need to understand, these systems are very chaotic and nonlinear, which means that like I'm sure a lot of people have heard about the butterfly effect. It is debatable how far it is true, but there are definitely some merits to it in terms of a change in initial condition could really change in could bring about a big change in the final outcome. So and this kind of helps in identifying what initial changes can affect what outcomes across the globe. And I highly recommend reading this paper. And this the application area for this particular work is in to understand interplay of these competing physical processes, just so that we can develop a much better understanding of the entire phenomena. So the entire idea of machine learning and climate would be not to be competing forces, but to kind of use and learn from each other. Whereas, like in this case, for example, machine learning can help us identify unseen patterns or previously not well understood patterns using some of the state-of-the-art tools, and vice versa, like that. So lastly, before I end, I just wanted to briefly touch upon this is that if you are interested in this particular space and would like to learn more or contribute more, there are a lot of avenues where you could do that. For example, climate change AI, where you can actually get data sets that you can run these your models on or build your experience on climate data. and you will also find a community to kind of interact with. Microsoft AI for Earth kind of gives out grants in case you're interested or have an idea that you want to, use machine learning for. You can definitely look up their website. Climate informatics is another area, another competition that you can actually use to, see what the community is doing, and they have some of the state-of-the-art results in this particular space. So yeah, before I end, I wanted to thank my collaborators and mentors at Lena for their help and support, and with all things climate. Yeah, that's all I have for today. So thank you so much for your attention, and I can take any more questions if you have.
All right. Thank you so much for this talk. Like, you're clearly very, very passionate about this topic. And like, thanks for sharing ways that people can participate as well. We do have a couple of questions here. So one is about the submodel calibration again. Like, they just wanted to understand kind of the main kind of use case for this. Is it to tease out some, some sort of interactions that might not be able to be teased out in like a whole composite model or something like that?
Sure. So I'll talk about the example that this kind of deals with, and that's a very good question. So this kind of deals with an example of geophysical turbulence. Geophysical turbulence is the key driver of energy and mixing. Mixing is, you can imagine mixing of nutrients or things like that in the ocean, and energy is the change in kinetic energy, and it's which kind of leads to how the energy kind of flows within the ocean, for example. So this kind of deals with that, and it's pretty much applicable to the atmosphere as well. So the idea here is that we train this model on so the current state of the art solutions, the submodels that there are. They can only predict well in particular regimes, say, for example, areas called weak stratification or strong stratification. There is no model out there that can predict between, the entire range between weak and strong stratification. And by stratification, I mean the difference in the density, for example, within the ocean. Because, if as you go deeper down in the ocean, the density changes, the salinity changes, things like that changes. So it is very important that a model can actually correctly evaluate for that. So this kind of approach, where we have physics information embedded in the system, here we have we deal with an entire range of stratification, from very weak stratification to very strong stratification, and then we predict it on an intermediate case, which is the case that you see here. So the effort at the end of this is that we developed a model that can actually transfers the range of stratification in the ocean, for example, and can predict the right amount of certain characteristics or quantities of interest that we need, that can be fed back into the global circulation models for accurate representation of that particular physics of stratification, for example, which is a very, very minor component of a big global model. So yeah, if that helps to give you any perspective.
Yeah, that makes a lot of sense. Thank you. I guess in the interest of time, we'll ask the one last question. So you mentioned that traditional maybe methods of modeling have high costs associated with them. What kind of is the cost that you encountered or that is common in the climate science field?
Sure. So typically, like, to give you an example, to run one big GCM model simulation, you would need a machine called Summit, which is a GPU machine out of Oak Ridge National Lab. And they run like for weeks and weeks on multiple hundreds of GPUs to make one simulation done. And that is the cost we're talking about, because they're trying to solve very expensive partial differential equations, where you have matrix inversions, where you have all these different processes that kind of like feed into one another. So at the end of the day, because one could either accelerate some of those things using machine learning, and there is a lot of work that is out there, or else you can just replace some parts of it using machine learning, so that you are bearing the cost at training time, but for inference you are paying a very cheap cost. So if to give an answer, like it is like thousands of GPUs for weeks and weeks to give one particular good, very high fidelity simulation.
Gotcha. Thank you very much, Peetak, for the talk.
Thank you.
I encourage people to, reach out or check out the links that Peetak has linked, and we will upload the slides afterwards on the website as well. So thank you very much, and hope you all enjoyed. Take care.
Thank you.